Hello YouTube, and welcome to another video in our distributed computing LLM series. I wanted to start this video off with an apology to my fans, to the machine learning community. I want to say I'm sorry, because this model sucks. This model is bad. Horrible. Who would have known that machine learning is such a computationally expensive, both in cost and time? Not me. Who would have thought? So I wanted to talk with you today about what I learned, because this was certainly a learning experience for me. Learning about Spark, learning how many roads must a man walk down before he absolutely loses his mind, how to configure your clusters for optimal results, and how to not obtain them. So anyway, let's jump right into it. So first I want to sort of go over what the workflow is, what you're going to be seeing. We've got about 13 steps going on in our program to train this model. We're going to parse our initial arguments. This is just going to be the input path, the output path, where we're getting our embeddings from homework 1 and a simple configuration file. After we initialize the Spark context and we load the configuration, all of the embeddings, define the parameters, which I will go into more specific what those parameters are. We're going to load and process all of our sentences from an input file into an RDD so that it can be processed distributedly. And then we go on to create some sliding windows, batch them, and then train the model. And that's really it. That's all it comes down to. So how could it be so difficult if it's so simple? It could be summarized in 13 steps. If you want to have meaningful results, you're going to have this thing running for several days, weeks, on a massive data set. Before I realized how much time this was going to take, I was training it on a meaningfully sized piece of data, a subset of the original input size from when we were doing word to vec. But it plateaued with like a training score of around 35. We were not getting anywhere. So instead, let me show you what we will be training with. Yeah. So originally I had a whole bunch of sentences. I was training them on about 200 epochs because I thought that's a big number. Yeah, no. Even just this still doesn't converge well at only 200 epochs, and I can tell you why. It's our vocabulary size. We're using byte pair encoding with pre-computed embeddings. I'm using the smallest one that I saw, which was 50K. That means that our one-hot encodings are IND arrays of 50,000 units. This is huge. This is massive, especially when our real vocab that we're working with is like 8 words. Our embeddings from homework 1 are fine. I can walk you through what we did for that. But you know what? Let's actually kick off this process because it's a bit time consuming. Let's see. So here we are. We're running at about 20 hours, which has cost me, let's see, what are we at now? Oh, beautiful. $23. So I guess to recoup the cost, you might see me begging outside of Fang, the Fang headquarters, panhandling, saying, "Please, I know Scala, please," in order to recoup my losses here. I'll fully admit that 10 of those hours I accidentally left it while I was sleeping. Anyway, so we're going to restart one of these steps Oh, you know what? Let me show you how to configure it first, because I had this running before the video for a couple hours, 200 epochs. That's the one that I'm going to show you. But obviously we don't have that kind of time. So I'm just going to show you what training on 3 epochs looks like. The first thing that we're going to do is we're going to upload the new configuration file. Here it is. So what are we uploading here even? So your hidden size, this is how many neurons are inside of your hidden size layer. If we go over here, your LSTM layer. I've got 2 so that it's able to memorize a little bit more data rather than just generalize, because we don't have enough data to make generalizations with. We are doing one sentence 100 something times. So we really, if we want to see results, we just have to memorize the input set. And that 256 corresponds to the amount of neurons that will be memorizing stuff. We could go higher, but then it would take twice as long and I wouldn't be able to record this video at all. Our learning rate, usually you would have it at 001, but again, small data set, I have to bump this up so that it learns a little bit higher. We use Atom for the learning rate, so it does actually fluctuate. It doesn't stay at just this number. But I'm setting it to a slightly higher default just because we're running with such a small input size. Batch size 32. This was just, again, this was a speed thing more than anything, to package all of the data a little bit, more on top of each other. The fact that every sliding window is basically the same thing, it really doesn't make too much of a difference for learning. Because it's not making generalizations over different windows in the data set. It's the same windows over and over again, just packaged on top of each other. The sentence is short, so I picked a shorter window size. And then for demonstration purposes, we'll have 3. But I've got a model that I downloaded before recording this video, running on 200 epochs. This Spark configuration stuff here just tells how many batches it's going to be processing, or getting the workers to process at a single time, and then averaging them. This I got from the demo file, the pseudocode that was provided to us. And we're actually going to be using some of that pseudocode for the transformer model to check the output of the model. Anyway, let's get this started. So we're going to clone the last step. It's got the new config. These settings here, we don't really need 6 if we're going to be training it for such a short of time. These were some settings I was messing around with when I was running into speed and memory issues. One issue that I ran into was with the network timeout. Sometimes when I was training on like 4,000 sentences, what would happen is it would take so long that it would kill the node before it finished due to timing out. And then it would start up a new one to finish the computation, and then it wouldn't. It would time out again. So I increased the timeout a bit higher. This is not relevant to this test case. I have completely given up on training on large, meaningful data, and we're instead just testing it on a single sentence. So let's clone this. And we'll let that go for a bit. While we let that go, let's talk a little bit about the code. So the 2 main functions are actually really the one main thing is we are creating sliding windows using the embeddings from homework 1. That was the big part of this assignment. And what that means is we're going to take in an input sentence of some window size, and we are going to load the embeddings in from memory. In an earlier step, we convert these embeddings that we loaded from memory into positional. We also turn them into unit vectors, so that the magnitude of these embeddings doesn't really matter as much. We're more looking at the directionality of them, since that's what embeddings are really supposed to capture. Embedding map broadcast. Oh, that's actually something we should talk about. So how do we make this process distributed in the first place? Let's go to the actual file when we talk about that. We'll run through the step-by-step here. So after we've initialized the Spark context and we load our configuration, we initialize an embedding map. And this embedding map is huge. We generated about, I think, 4,000, either 3,500 or 4,000 embeddings from homework 1. And so we're initializing this map, and we're going to get it back by saying get embedding map from this object. And then we're going to broadcast it. Why do we broadcast it? If you don't, you will run into huge memory issues trying to share this massive map back and forth with the worker nodes. So originally what I was doing when I was running this locally was the embedding map was just a part of sliding window with positional embeddings. It was just one of these private variables. But the worker nodes don't have access to these after they've been initialized. They get the default values, but they're empty. Only the driver had those initialized. So in order to share them, what I was doing is I am using Spark to broadcast this map to the worker nodes. This allows the workers to have access to the reference, or I'll pass the reference to this map, and the workers are actually able to they have it in memory, whereas before they did not. So first we're going to get the file content. That's just all of our sentences. We use Spark for that Spark text file. It converts everything in the input directory, sort of like Hadoop, just line by line, and we turn it into an RDD. This allows us to iterate over them and have the workers create sliding windows of the embeddings in a distributed fashion via flat map. So what happens when we do that? We are going to create a sliding window, including the target token. And what we're going to do is we're going to tokenize embed that input window. We're going to dereference that broadcasted map with that value so that now the worker has dereferenced it and it has access to it in the tokenize and embed function, which just says, hey, look for this particular token inside of this map and give me the embedding. So after we fetched it, if we didn't fetch it, we didn't find it, we're just going to come up with a random one, and then we're going to shape it to be the proper size because it's just going to give us a one-dimensional array. We need a two-dimensional array with one row, and that allows us to stack them on top of each other. So then we have a full sliding window. We get the embedding for each one of the tokens, turns it into an embedding vector, and we stack them on top of each other. Pretty simple stuff, nothing too crazy. We then positionalize them with positional embeddings. This is just a 1 0 1 0 1 0. This allows the model to see like, oh, these embeddings have an order to them in this sentence. And then we just return the normalized position aware embedding. That's pretty much it. Nothing too crazy. So what happens after that? After we have we flat mapped all of these sentences into positional embeddings, we have to batch them because our LSTM requires batched data. We use map partitions to parallelize this process so that each executor has their own section of data that they can batch, and then we're going to work with that batched data. You might notice we're using cache and count. What that does is instead of lazily loading the sentences and the windows, we're going to get them immediately. That allows us to create, and then we're caching them just so that they're stored in memory and they don't have to be recomputed. I think in our case we only ever actually run them once, but this also allowed us to have some meaningful metrics printed out in the correct order of how many windows ended up being created and how many batches. Once we've done that and we set up our model for Spark, we run some epochs and we get some data about them, and we should be able to see that already. I don't think that should take too long. We've only done 3. So if you want to look at the Spark data, very overwhelming, but what's printed out, oh, okay, it's still working. We've created 100 sentences. From those sentences, we have created 5 sliding windows per sentence, so we've got 500 total windows, and now it's going to start batching them. And let's actually see what these steps look like visualized on the Spark history server. This is pretty neat to see, especially on the larger data see how it was processed. Anyway, let's take a look. Those were all of the failures. Let's take a look at where we're at right now. Oh. Might have finished already. Let's take a look. That was fast. Waiting, yeah, well... Oh, it finished. That was fast. So of those 500 windows, we created 14 batches, and you can actually see the training loss start to decrease pretty rapidly, ending with 20% accuracy, not bad. Funnily enough, when I pre-trained this before recording this video, this was the same accuracy after 200 epochs, so it really doesn't get much better. That's what I was saying before. I failed you guys. I really just... I don't get it. I don't get it. Yeah. It just doesn't make a difference. It does not make a difference. But it's distributed. We saw it. You saw it right there. Let's now that it's done, we should be able to... I do still want to check out what that looked like. Here we go. So what was Spark doing? It added some executors. We collect file util collect. This is when it is reading the input file from memory. We're going to turn, or reading, sorry, the embeddings from memory. We're going to turn it into a map. And this count, oh, wait, let's see. This is either reading the input file or the, you know what, maybe both. Not sure. But this right here are the, this is where it's learning. You can see the 3 epochs visualized right here. And then finally at the end we run a little test by taking the first 5 batches, and that's where it calculates that 20% accuracy score. It just goes over those batches and it sees like, all right, what's the expected? What's the actual? Is it right? You get a point. If not, you don't get a point. And then we get a percentage of points over total. Anyway, so this will be the first time I'm running this, the model with 200 epochs. So we are going to see it together for the first time in person. So we're going to run the transformer model. Our input sentence is the real stars in the sky. We are going to expect to see, let me take a look here. The real stars in the sky, we expect to see have no points. Let's find out if that's what we see. Moment of truth. I beg your finest pardon. Oh, wrong name. This one's just called model.zip. The real stars in the sky. Almost lost my composure there, guys. Well, anyway, there you have it. That's my video for you today. I hope you liked it. I hope it was informative. If you have any questions about Spark, send them my way. Have any questions about machine learning? Don't. Till next time.